Name the two types of potential energy involved when a mass spring system performs vertical simple harmonic motion. So a mass spring system obviously has a spring, so there would be elastic potential energy. It's performing vertical simple harmonic motion, so it's going up and down. Therefore, there would be a change in GPE as it rises up and then falls back down. So the two types of potential energy would be elastic potential energy and also gravitational potential energy. Describe the energy changes which take place during one complete oscillation of the vertical mass spring system, starting when the mass is at its lowest position. Okay, so let's consider this to be our equilibrium position, the place where there is no resultant force. We'll consider the mass in the bottom position. It then moves up to equilibrium, moves up to the top, and then it comes back down again all the way to the bottom, and that will be one complete oscillation. So, at the extremes, so at the top and at the bottom, kinetic energy is zero. And the reason for that is because the oscillator, the mass spring system, has paused momentarily before it returns back to equilibrium. So for instance down here, the mass goes down, it stops for a split second and then comes back up, so kinetic energy is zero. Same thing here, the mass goes to the top, pauses momentarily, and then comes back down. So at those two positions, speed and therefore kinetic energy are zero. In the middle, kinetic energy is a maximum value. One way in which you can think about that is to think about the force on this mass as it moves up and down. So if we think about the conditions for simple harmonic motion, force has to be proportional to displacement and in the opposite direction to displacement, so it must always act towards equilibrium. So if we think about the mass in the bottom position, to begin with, the force is acting upwards and it is moving upwards. And that force will continue to act upwards until it gets to this point. So as it moves upwards, the force is upwards in the same direction as velocity. That force causes it to speed up, speed up, speed up. When it gets to this point, the force is zero. Then it moves upwards, and when it's above equilibrium, the force acts downwards. So although it's still moving up, now the force is opposing motion, and therefore the force will slow the mass down. That force starts to act once we pass equilibrium. So up until equilibrium, up until the oscillator gets to this point, force is in the same direction as velocity, causes it to speed up, it reaches a maximum speed here, now the force opposes motion, and now it will start to slow down again. So that's why KE is a maximum at equilibrium. For the potential energies, so at the bottom, elastic potential energy is a maximum at the bottom, and the reason for that is because, so this mass is attached to some kind of spring. Let's say here's a ceiling, here is our spring. The spring will be the most stretched when the mass is in the bottom position, so we have the most elastic potential energy. As it rises, that elastic potential energy decreases and it gets converted to gravitational potential energy. So here, the mass is in its highest position, so GPE is a maximum. So what's happening is, at the bottom, we have maximum elastic potential energy. As it rises, kinetic energy rises, as does GPE. Kinetic energy peaks in the middle at equilibrium and then decreases to zero at the top, and that's where GPE peaks. And then the opposite happens in reverse. So GPE gets converted to elastic potential energy. In the middle again, kinetic energy peaks. Figure 3 shows how the total potential energy due to the simple harmonic motion varies with time when a mass spring system oscillates vertically. So we have total potential energy on the y-axis, and then we have time in seconds on the x-axis. The question is asking us to state the time period of the simple harmonic oscillations that produces the energy time graph shown in figure 3. Explain how you arrive at your answer. So, for simple harmonic oscillators, whether it's a pendulum or a mass spring system or any type of simple harmonic oscillator, 2 full cycles, so that takes us to 0.8, 2 full cycles of either potential energy or kinetic energy corresponds to 1 full oscillation of that oscillator. So in the case of a mass spring system, let's say it starts at the bottom, this full 0.8 seconds, 2 cycles of that potential energy graph, corresponds to the mass spring system going from the bottom all the way to the top and then back down to the bottom again, which is one full oscillation of that mass spring system. I'll show you why. So going back up to the diagram that we had before, in the bottom position here, that's when potential energy is a maximum. So that corresponds to this peak here. It then rises, reaches equilibrium. That potential energy gets converted to kinetic energy. So the overall potential would be a minimum over here. That corresponds to 0.2 seconds. It then rises all the way to the top, and then GPE is a maximum. That's this peak over here at 0.4 seconds. So what we just saw is that as it rises from this position to here, that is 0.4 seconds on our graph of potential energy against time. Rising all the way to the top is half of an oscillation. The full oscillation takes us from the bottom to the top and then back down again, so we will need to have another cycle of that potential energy curve. So for this, we would say that for each oscillation of our mass spring system, there will be 2 full or 2 complete cycles of potential energy against time, and that's why our time period would be 0.8 seconds for our simple harmonic oscillator. Sketch a graph on figure 4 to show how the acceleration of the mass varies with time over a period of 1.2 seconds, starting with the mass at the highest point of its oscillations. On your graph, upwards acceleration is positive, downwards acceleration is negative. We don't need to have values on our acceleration axis. So it's a period of 1.2 seconds. That doesn't mean the time period is 1.2 seconds. The time period is the same as before. It was 0.8. It says how the acceleration of the mass, so it's still referring to the previous scenario, the time period for that was 0.8. We're sketching the acceleration time graph over 1.2 seconds. Let's consider the scenario. Here's equilibrium. It says in the question that the mass starts at the highest point of its oscillation, so it has the most displacement from equilibrium up above equilibrium. For simple harmonic motion, force is proportional to minus x. So the force acts downwards towards equilibrium, and because it has the highest distance away from equilibrium, it will have the highest force, because force is proportional to displacement, and therefore it will have the highest acceleration as well, because F is equal to ma. So acceleration is a maximum value to begin with, but it is a negative value, because acceleration acts downwards. It says downwards acceleration is negative, so we have a max negative acceleration to start with. The time period is 0.8 seconds, so this value should repeat again as 0.8 seconds. Whenever we're considering acceleration, velocity, or displacement against time, it's either going to be a sine or cos, or minus sine or minus cos graph. Those are the graphs that you consider in A-level physics for oscillators. If we're starting at max negative acceleration, that means that we are considering a negative cos graph. That's the only graph that starts at a max negative value to begin with. It's a negative cos graph, time period of 0.8. So we'll have our positive peak at 0.4 and at 1.2. It'll hit equilibrium at 0.2, 0.6, and 1. And then we can just connect the dots. Draw a cos graph. And this will be our final answer. For C part 1, the mass of the object suspended from the spring in part B is 0.35 kilograms. So part B was this scenario here. So what's unique about this scenario is the time period, again, is 0.8 seconds. That's all the information that we're effectively told here. Time period is 0.8 seconds. What are we trying to work out? We have the mass. We want to work out the spring constant of the spring used to obtain figure 3. Figure 3 was the graph that we had here. So what is the spring constant of this spring? We know the time period is 0.8. And again, we know the mass is equal to 0.35. We want to state an appropriate unit as well for the answer. Okay, so equation that we're using here, time period is equal to 2 pi root m over k. We're trying to work out spring constant. Let's square everything. T squared is 4 pi squared. Square root goes away. If we rearrange that for k, just switch the k and the t squared, we get k is equal to 4 pi squared m over t. Oh, that should be squared. put in the 0.35, put in the t is equal to 0.8 seconds. We get 21.59. So it looks like we have 2 sig figs over here. So then I will give my final answer to 2 sig figs as well. So 22, and the units would be newtons per meter. If you're not sure why those are the units, think of F is equal to kx. K is then equal to F over x. That's newtons over meters. And finally, for C part 2, the maximum kinetic energy of the oscillating object is this, 2 times 10 to the minus 2. Show that the amplitude of the oscillation is 40 millimeters. So maximum kinetic energy is equal to half m maximum speed squared. Vmax, maximum speed, is omega a. So this will be a half m times omega squared a squared, subbing this omega a into what we have here. If we rearrange that for amplitude, so we get Ke max times 2 divided by the m omega squared is a squared. A is then equal to the square root of that. So 2 times, kinetic energy is 2 times 10 to the minus 2, divided by m, which was 0.35. We had that earlier. That was the mass given over here, 0.35, and then multiplied by omega squared. So omega is 2 pi f, or 2 pi over t. T was equal to 0.8. So omega is 2 pi over 0.8, which is 7.854. So this would be 7.854 squared, as it's omega squared. And this gives 0.043 meters, which is approximately 40 millimeters. What we have here is about 43 millimeters, so that will be approximately 40 millimeters.